Okay, so we're going to look at a very important area, and who knows where this is going to end up. It may completely change the infrastructure of the internet towards a decentralized approach, or it might end up being a new finance infrastructure. Who knows? But really, we need to understand the scope of blockchain and cryptocurrencies. And at the core, really, is the usage of public keys. So our public key encryption showed that we could actually create trustworthy transactions by signing with our private key and proving with our public key. So when it's distilled down, really all that blockchain and cryptocurrencies are is a way for us to digitally sign a transaction and for that transaction to be provable. So we'll look at cryptocurrencies and their usage, mainly at the technology involved. Then we'll look at one of the most active cryptocurrencies, which is Bitcoin, and along with that, we'll look at the blockchain that's created from the Bitcoin. Then we'll look a bit at the mining process and how we create a consensus. Then on to second generation blockchains such as Ethereum, which use things like smart contracts. And then eventually we'll look at some of the other options that are around that create what are called permissioned blockchains, and that's Hyperledger and also infrastructures that allow us to be able to interconnect blockchains, and that's something like the Polkadot blockchain infrastructure. So here we are. So we're at week 12 now, and we have our guest lecture this week, Scott Helmy, at 1 o'clock. So hopefully you can join that. And we're really focusing on the final part of the course, and that's the coursework hand-in on the 14th of May, and that's worth 60% of the overall marks. So hopefully you've all had feedback on your first test. If you haven't, then give me a shout today and we can go over your test. And also in the lab today from 11 to 1, there is a blockchain lab that you can do. But obviously if you want to pop by and discuss your coursework, then please just send me a little message and we can go over your coursework. There's an evening session tonight at 5:30 till 7 o'clock, and we'll just go over what we did today, and then there'll be an opportunity to ask questions around the coursework. Does anybody have any questions on that? Any queries? No? Good. Okay, so we're going to look at cryptocurrencies. Okay, does anybody know what that is? That photograph is?
A lady standing in front of a Christmas tree.
Okay, that's that's one interpretation. That's exactly right.
Probably the Merkle tree.
It's a Merkle tree, yeah. So the great leader Merkel standing in front of a Christmas tree there. Does anybody know how that relates at all to anything that we're going to cover today?
Ralph Merkel's Merkle trees.
That's right, yeah. So Ralph Merkel proposed a tree structure where you could hash data values and then create what's called a root hash, and then that root hash would then prove immutably all of the data that was inside the hash. So here's what he created. Have a look at the patent if you have time. It's a really cool patent. While other patents go on for 20, 30 odd more pages, Ralph's patent at the time basically was a diagram that looked a bit like this. And it was such a wonderful innovation, and applies to many areas such as hash tables and so on. So it's not just in blockchain, but we see it within GitHub to keep version control and so on. And really what happens is that we have data elements, and as we saw before, we can hash each of these data elements. We take these two together to create a hash. We then create the hash of these two elements, and then we create the hash of these two elements, and then eventually we create an overall hash. It is now not possible to change any of our data elements. So I can't come along and change UK to Germany or something like that there. It is now immutable that the root signature is the aggregation of all these other signatures. I can also prove to you that it was the UK that was the data there by showing you the part of the tree that takes you to the point of that hash. So in a blockchain infrastructure, what we do is we create that roots hash, and we store that in our current block. So the block itself will contain the data elements that we are verifying, and then what we do is to make it even more immutable is that we take the hash from the previous block and add that to the current block, and then we take the hash from the next block and then add that to the current block. In this way, we create a chain of blocks. So once we create our first block, normally known as the Genesis record, then that's the starting point. Next block that we then create, we take the hash from that one, we add on the current hash, and we do a look ahead on the one that's coming next. And in this way, we create a chain which is immutable and where it can't be changed anymore. The whole of the system is up to date. And if we define these as timestamps, so let's say in Bitcoin, roughly 10 minutes between each block, then it's also mutable from a timing point of view that if I did a transaction and that transaction appears in that block, then you now have a timestamp to see when that transaction actually happened. So in this way, we can actually create a more trustworthy infrastructure using this Merkle tree. So who's 12 years old to recently? Well, it's actually Bitcoin, and it feels like Bitcoin has been around for a long time, but it was created in 2009 and has basically worked ever since. We've been tinkering with it along the way and trying to address its fundamental problems, but basically the white paper that Satoshi Nakamoto created is basically what we have now. As we'll see, it's not a perfect system and it consumes vast amounts of energy, but it works and it is a cryptocurrency and it can be traded. But as we'll see, it's probably a long way off from being anything that we would build an infrastructure from. So it's created by Satoshi Nakamoto, and that probably isn't him. Who knows who Satoshi is? I'll propose an idea a little bit later. But if anybody knows who he is, then there are a lot of Bitcoins waiting to be released that relate to him. So he created a white paper, created a prototype using Windows, a Windows system, and with C++. And he worked with someone called Hal Finney, who who died a few years ago, unfortunately. But Hal Finney did a lot of the peer review on the first versions of Bitcoin. I was generally involved in the crypto community at that time. It's probably not the case that Hal Finney is Satoshi Nakamoto. Does anybody know who's proposed as Satoshi?
I heard Elon Musk.
Elon Musk, yeah, that's a wacky one. Yeah, that was that's a possibility, I suppose. But I don't think it's likely, but that's fine. Anyone else?
I think it's you, Bill.
Do you think I would be lecturing just now?
It's a good cover. It's a good cover, I tell you. You know.
It could be, yeah. Okay, yeah. I've just using Hashcat to release my private key. You wouldn't believe the number of people who contact me saying they've lost their password for their Bitcoin wallet, and could I help them release the private key? And you can't tell if this is a hacker or if it's a genuine thing. So there's and now that's Bitcoin is worth a lot of money, then obviously it's worthwhile. But obviously Hashcat, as we've seen, is very good. But obviously it's a slow cracking method because of the hashing method that's used for Bitcoin wallets. But Hashcat can do it quite well. And anyone else you want to propose?
Nick Szabo.
Yeah. Anyone else? Adam Black was pinpointed. Probably the closest was the Australian. Anybody know the Australian's name? I forget off the top of my head. I'll send you it. It was certainly someone that was involved in the community, but there was also what were called the cypherpunks at the time, and they were looking to build an infrastructure which changed the banking infrastructure, and I'll cover that in a little minute.
Craig Wright?
Craig, that's right, yeah. Good old Craig, yeah. You'll find some really great videos online for Craig. He
was interviewed, wasn't he, a couple of times?
He was, yeah. He could sign one of the transactions. I can't remember, something like the 10th one, but he hasn't produced the signature on the early ones, so he hasn't really proven. Whoever can show the private key for these ones that have gone unclaimed, then that is obviously pinpoints the person that created it. So this was the Genesis record, and 50. So I think we're up at about $50K. So that's worth, that one transaction is worth a lot of money now. So this is the Genesis records. We define a height, and that's really the block number that we are looking at. You can see it's a very tiny little block. It's only about 200 bytes long. So the original spec was that we had a 1 megabyte for each block, which we thought was going to be enough. But then what was happening a few years ago was that just like a train, if the train is full, then you've got to wait for the next train to come along if it has a certain number of carriages. So what they did, and it was worrying because this is every 10 minutes, and if I make a transaction, I don't see my transaction happening for about 20 minutes or so. So they made an update which allowed us to break out the 1 meg limit for each block, and it's still around that kind of region just now, but you can see that small one there. So there's a nonce value that goes in there, and the nonce value is the seed that produces the hash of the overall block. And you can see in this case there's no previous block, of course, but there is a next block. So this is block 1 that we have here. This is the current hash on it. And what's significant, can you have a look? I don't know if you can see the hash. Can you tell me what looks a bit strange about that hash? This one here.
Is it the fact that there's the lead preceding number of zeros at the
That's
beginning,
right.
which looks non-random?
That's right, yeah.
That's a problem, isn't it?
Yeah, but it's good. It's what's called a proof of work. You've got to create a consensus on this, and it's got to be a fairly instant consensus. So lots of entities have got to come together and say that is a valid transaction, or that is fraud, that is double spend. So what happens is that the miners race to find the nonce value. When you hash the whole lot, when you add the nonce value onto the transactions, you end up with a hash which has got preceding zeros, which is actually quite difficult to do. When you think about it, if you keep hashing, you've got to go through a lot of nonce values to get a hash that's going to have all these zeros. So do you know what type of device is used to be able to do that kind of thing?
ASICs are good for that.
ASICs, yeah. ASICs and is like embedded hashing and so on, optimized, and obviously GPUs. I think there's been problems in getting access to GPUs fairly recently, and GPUs are used fairly extensively in Bitcoin and Ethereum mining because these GPUs are very good at doing hashing and obviously generating the random values. Okay, so that's what the block looks like. There's only one transaction in there. It's got an immutable timestamp in there. There's a difficulty level and so on. There's not much else to see in that. And there's the Merkle root, as we said. So that's going to prove the block from there. Okay, so basically it was a hodgepodge of different crypto methods, but it kind of worked. And it was really part of the cypherpunk movement. Eric Hughes, Tim May, and John Gilmore, who proposed that we could move towards what's called a peer-to-peer infrastructure for blockchain for a blockchain approach. Satoshi kind of picked the right things. He picked elliptic curve, which was a good choice at the time. He picked what was called SEPT 256K1, which it seems to be a pretty good elliptic curve, fairly secure. We've not had many problems with it. There has been problems with the signature. It uses, or it has used, a signature called EC elliptic curve DSA, which has had a checkered past. Does anybody know where there's been problems with EC DSA in the past?
Is the choice of certain values?
Yeah, that's right.
That might not be the most optimal values given. It renders it more liable to be broken.
That's it. If you don't use a random number generator, a good one, if you generate the same random numbers within a timestamp, then anybody can crack your private key. So nonce reuse is a bad thing, and anything that isn't a random number can be bad. There was a classic one. Does anybody know about the Sony PlayStation fiasco? No? Well, Sony picked a private key of, I think it was 9, which you could maybe say was a random number on its own, but certainly it isn't random. So for some reason, when they were signing for the PlayStation, they used a private key of 9. So the one thing that you shouldn't do is to be able to create something that isn't quite random. So somebody once discovered that, and obviously what they could do is take the Sony PlayStation and easily sign the operating system or modify it and sign it with a private key of 9. So if a company like Sony can make such a mess, then you can see you're in trouble. It also happened on Android devices that the random numbers were not random, and quite a lot of people lost their cryptocurrency because it was fairly easy to discover their private keys from guessing, because you can keep guessing what the private key would be. And there's actually a research paper that shows quite a few addresses that are under 1,000. So who knows how they've been created, but some developer somewhere has maybe just taken a private key for test, but forgotten about it and then released it out. But there's a major one from Google where a lot of wallets were actually hacked because of this Android bug. So it's got to be really carefully looked at, and to make sure that ECDSA isn't weak from the way that we're generating our random numbers. Okay, so this is the paper, and it's a really good paper, and it's readable. Does anybody know what the Ethereum paper is called?
Sort of towards a better.
Yeah. No. Yeah, just what it's commonly known as. It's commonly known as the yellow paper. So it's printed on yellow paper, even though it's a PDF. It's not a good read. If you're going to read one paper, then this one is really good. So with the Satoshi paper, he lays out everything. She lays out everything to do with Bitcoin, and really that has become alive. Everything that was said in there has really been since implemented. And it was Eric Hughes and Tim May and John Gilmore that could really propose a different way of transacting. And it was around the time of the banking crisis and so on, where banks were getting very rich and lending lots of money to people who maybe shouldn't be lended to. So they looked at a different infrastructure for financial trading that might not involve a bank to be an intermediary in between. And then it was obviously Rivest, Shamir and Edelman who came up with public key encryption. They used RSA, and Satoshi used elliptic curve methods, but the basics of it was that we could use a private key to sign, and then we could prove with a public key from there a much more trustworthy infrastructure. So this was Satoshi, or what was thought, and actually it's well known now that isn't actually Satoshi. He does appear in the telephone directory in the yellow pages. In the area that I think that Hal Finney lived in, don't quote me on that, but I think if you look where Hal lived, there is a Satoshi Nakamoto in close vicinity. So perhaps they just looked up the telephone directory and found a name, and that was the person. So I think this is an interesting one. This was sent on the 1st of April, so you can take that one with a pinch of salt. Okay, and it's a fairly profitable crime to be able to crack Bitcoin wallets, and there's been quite a few hacks on exchanges, because an exchange can have wallets there, and because there's no intermediary such as Visa, if you make a payment to the wrong address, then you have very little chance of getting the funds back again. So there's been some very famous ones, and especially around initial coin offerings, where hackers would hack into the database of people who were going to pay for the coin offerings, and then just before they were to make the payment, they would send an email to say, please could you send it to this Bitcoin wallet, and obviously it wasn't the right one or not. So within these systems, so there was a major one around Ethereum, and what happened with Ethereum was there was a hack of Ether, and it was thought. So the opportunity that we have is to do a rollback. So if you have a hack here and you're currently here, then one opportunity is to go back in time and then create what's called a fork. So the fork will start a new set of blocks or a new chain, and then an existing one withers because there's no consensus behind it. So they looked at that, and really, if we started to do that, really we'd be in big trouble because anybody could start to roll back, and who has control? No one should have control of the blocks. So it was decided for Ethereum that we went with Ethereum Classic that had the hack, and then we went with the new Ethereum, which was the derived cryptocurrency from here, and both still exist, and you can still purchase both. But that's when you create a fork, obviously when you get a major hack like that. So an intruder will often go looking for anything that looks like a wallet. So maybe in an Android device, wallet.dat.zip, backup, and so on. So an intruder could scan a system looking for these wallets, and then you obviously use Hashcat to be able to crack these open. So this is an example of a log for a scanning agent that's going and scanning for publicly available wallets on the website. And there's a lot of these crawling agents. So my advice is always to protect your wallet with hardware protection and biometrics, and don't put it on a website, and don't have it on a crypto exchange where somebody could discover your wallet from there. Okay, and there's well proven honeypots examples that people have set up these wallets, and someone has went in and to try to discover them. Okay, so there's lots of issues that we need to look at for a future world which is more trustworthy. And probably one of the key ones to look at is, what does ownership of something, of an asset, actually mean? So that was my car there. So how can I prove that I own that car? Well, it's registered somewhere on a database, and that's probably the only place that you can actually prove that. We can also create a piece of paper that could prove that too, but it isn't really a trustworthy infrastructure. So perhaps increasingly what we'll see in the future is our tokens, or digital assets which are signed. In art, they're called NFT. Does anybody know what NFT stands for?
Non-fungible token.
Yeah. So who knows if they're going to take off or not, but it makes a lot of sense to have a token related to a piece of art that's actually digitally signed, and then it's actually proven from that. So really we could start to kind of transact with tokens. So when a car was created, it it would have a complete history. You could see all the sellers and so on, but obviously we have privacy problems related to that. But we could actually start to transact tokens in the same way that we transact sort of assets. Then you have things like consents. Even defining a physical border these days is extremely difficult in a modern world. And that really looks to whose laws do I comply with? So if you're dealing with Amazon, is it the laws of Luxembourg that you're dealing with? If you're dealing with Facebook, is it Californian law and so on? In some places in the world, they might ban cryptocurrencies, but you might be trading them in another country and so on. So the whole concept of physical borders and laws and trading in a digital way really changes completely with these new digital assets. And probably one of the big ones is that why does fiat currency even exist in this modern world? It was used in the past for governments and states to be able to control their economy, and they could release more money or take it back, and that generally created allowed them to control their economy. But without that, you can then, with a cryptocurrency, have a currency which isn't tied necessarily to a fiat currency, and then the whole idea of nations and governments controlling their economy becomes redundant.
Bill, one question on that. Obviously the finite limit on the number of bitcoins, 21 million, and then the paper sort of says this makes it inflation proof because we can't just release more and more. I mean, the evidence is just over the last 10 years it definitely isn't inflation proof because it's massively inflated just because of speculative investment.
Yeah, I think we've never really used Bitcoin properly as a trading mechanism. It's used then as an investment, unfortunately, and it probably isn't a good cryptocurrency for trading. So that I'll come on to this, but there are ones that are tethered to the dollar, and there are ones so you can run your own cryptocurrency and run your own exchange and keep it. You can have a Napier token that you will always give $1 back.
Yeah, but that in itself is tied to a currency, which is one of those ones that the crypto community are criticizing for being stable. You know what I mean? But it needs that stability.
That's right. So what I could do is I could define a task for you. So I don't know, to sell a car, I would say it's one Napier token. So you're now relating it not to fiat currency, but you're actually relating it to an amount of work. But eventually, and I could trade that with someone else for some more. So you only need fiat currency when you cash out. And in a healthcare infrastructure in the UK, then the NHS really has all the funds. So you could actually have an NHS token which would relate to work, and you could trade that token, and the NHS would always cash it out eventually in some sort of currency. Sorry, were you going to add another?
No. It's just that really interesting point that about the Bitcoin not being inflation proof, but that was one of its claims. But by limiting, in other words, you can't just print money like governments can do in cases of quantitative easing and that sort of type thing.
Yeah, that's exactly right. Yeah. But it hasn't worked. You're right, and it's consuming too much energy. Okay, so we've got basically three generations. First generation, pretty poor. The Bitcoins and Moneros and Litecoins and so on. They have high transaction fees and fairly high transaction times, 10 minutes for Bitcoin. The second generation were much faster. They supported smart contracts. Vitalik proposed Ethereum, and it had a payment mechanism for the miners to pay them for the work that they did, rather than them all racing together. And it allowed you to be able to translate high-level code, Solidity, into a bytecode, just like kind of Java does, and to get a bytecode level that would run off the blockchain and could be trusted. But where it becomes interesting is when we move to a DAG infrastructure, or a direct acyclic graph that Merkle proposed. And that allows us to create multiple chains and multiple ways. So in this, we can actually create a whole tree of transactions at any given time, and we can almost get an instant consensus on the whole of the infrastructure. So for things like IoT, where we need instant consensus, because I need to know your blood pressure is at a certain rate without waiting 10 minutes, you need instant consensus. So IOTA and some of the newer blockchains are looking for this instant consensus, and where we can sequentially store transactions and not end up with these big blocks. It's still a long way in terms of being able to get the throughput that we would have with a Visa infrastructure. So Ripple is the closest. It's not really a cryptocurrency per se. It's more an exchange token. Banks use it to be able to transact between banks, and it's almost like a proof of transfer that you would have. But you can see that Bitcoin and so on still struggle against the might of Visa processing extremely high rates. But generally Ethereum is moving up. This is quite an old graphic just now, but Ethereum is looking to create new infrastructures, and more distributed infrastructures. The new Ethereum method looks at if you have two islands trading, then each island can trade on their own, and they would have a ledger, and that's the way that they would have transacted within their own island, and then they might start to trade between each other. So what you now need is the two ledgers on each island to show the local transactions, and then you have a ledger in between the two islands to actually define the trading between island 1 and island 2. If you look at the three ledgers together, then they create the overall infrastructure. So the new Ethereum method is looking to scale up. We thought we had broken Ethereum with CryptoKitties a few years ago, but we managed to cope with it, and it's still chugging along, but it is struggling a bit with fees just now. So, and Bitcoin and Ethereum aren't the only shows in town. There are other, probably better public blockchains. I'll explain the difference between public and what are called permissioned blockchains a little bit later. But you can see Bitcoin, 10 minutes for each block, 2,000 transactions per second. It's not a lot, is it? 100 gig about for the blockchain size. So if you run one of these, if you run a consensus node, then you may end up having to store up to 100 gig of data, and it's growing about 4 gig a month in there. Ethereum is a bit better for the updates, but it's still quite a large database. But you can see with these newer blockchains, we can get it down to a couple of seconds or so. There's a minute for that one, and this one's interesting because we can do 100,000 transactions per second there. What's also interesting is that we can create what are called sidechains, and sidechains allows you to store private data in a kind of a DMZ area. Smart contracts, as I said, is a kind of key element, and each of them have their own preferred language for implementing. Some support quite a few, but those are the kind of focus for that. Multi-signature I'll come on to in a little minute in there, but you can see they're all decentralized and that we can hit we can decimate the whole of the network. As long as there's one copy of the blockchain existing, we can still replicate that. So that's the big advantage, in that if we corrupt a central database, then that's it. But on the blockchain, we have so many copies of it, and it's updated regularly. We can kill all of them apart from one, and we'll still be able to recreate the infrastructure. Okay, so basically, if you thought about it in terms of that, it's like a 4T for Bitcoin. We improved with Ethereum with smart contracts, and we have the possibility of creating tokens in there. But really, blockchain 3 looks at what's called instant consensus, or near instant consensus, and also Byzantine fault tolerance. Does anybody want to guess what Byzantine fault tolerance might relate to?
Infinite ways of being able to reconstruct it if you lose part of the blockchain. That's like you referred to before.
That's right. I mean, often we might talk about if at least a third of the nodes are still running, maybe the other ones have been killed or taken over, then we can still create a valid infrastructure. But we've got to detect a baddie. So if I place a bad node or lots of bad nodes in here, can I sway all the other nodes to agree with my transaction? And that's obviously the problem that we've got. In most cases, it's proof of work. So if I need to sit on the Bitcoin network, then it's going to cost me time and effort to do things, and I might never get the consensus, so it's going to be very expensive to run my GPU network. If I eventually manage to get half of the nodes in the network, then I could then take over the network and I would own Bitcoin. So it certainly happened in the past, and we've got to watch that 51% infrastructure. But Byzantine fault tolerance means that we can, it doesn't matter if we lose nodes or if they're taken over, and then we can still create our fault tolerant network.
Phil, is that a problem for newly created coin architectures, that the smaller they are, the easier it is to do a 51%?
Yeah, that's right. So I think Facebook with the Libra, I don't know where they are with Libra just now, but they allowed others to come into the consensus network. So I don't know, you might have JP Morgan coming in, you might have a few independent nodes, maybe you would need 20 consensus nodes at the core of Libra, and everybody trusts those nodes because they've paid their money up front and they're part of the consensus network and they're trusted. If we find that JP Morgan is starting, say, I'm not saying that, but we say that a bank is swaying the currency the wrong way and creating fake or having too many bad transactions, we could kick them off the consensus network. So yeah, you've got to make sure that you have a good consensus and it's distributed and it's not reliant on one entity. We'll come back onto this. But what a lot of systems are moving towards is what's called proof of stake. Does anybody know anybody guess what proof of stake might relate to?
In proof of stake, instead of miners, you have validators. And to be a validator, you need to put some money or token up front. That will give you the right to sign the block based on some random algorithm telling when is your turn to sign. That's the core of it.
Yeah. It's also to do with that a node has existed for a long time and has been so trustworthy. So it's unlikely. So the worst nodes are the ones that just appear and then disappear. So proof of stake is all about making sure that I've been good in the past. So I have a good track record of doing good transactions. I've always done them fast, and I've always been reliable, and I haven't had any bad transactions and so on. So as you said, that's one metric, is that I've paid my money and I want to be there. So obviously that's a good part of stake. But being a good stakeholder, again, is all about being trustworthy. And the longer you're in the network, then the more trustworthy you actually become. Okay, so those are generally what are called Byzantine fault tolerance systems. So if we look at the basics of blockchain or a distributed ledger, in a traditional banking system, the banks have a ledger, and at the end of the day, they sign off the ledger. They look at all the incoming and the outgoing, and then they'll sign off on the ledger. And when you look at the two ledgers together, they will give you the complete log of all the transactions. If you bring all the banks together and you look at all of the ledgers, the pluses and the minuses, then you should end up with zero overall in terms of the overall movement in and out. Okay, so we have our bank, we have our sort code and our account, and our bank can hopefully understand what the sort code is. Obviously, we look at SWIFT and IBAN numbers and so on, but basically, we find a way. And does anybody know what the main finance infrastructure for banking is?
Swift.
Swift, yeah, Swift. There's been lots of hacks on Swift, massive hacks. They don't really do crypto that much. There was one recently that was 81 million. It just disappeared. It was the bank of. Does anybody know what bank it was that was hacked?
Is it Burma or somewhere over?
Nearly. It starts with a B.
It was the printer, wasn't it?
Yeah, it starts with Bangladesh. Did someone say?
Yes.
Yeah. Is that the printer?
Yeah. It was the most unfortunate place. They don't have 24/7 security operation centers or the best virus control. One of the poorest countries in the world, and obviously the intruders went for that bank and installed the backdoor Trojan that I think was used in the Sony hack, and they got away with 81 million, and they nearly got away with another 21 million, but they spelt the word foundation wrong. They had foundation, and it was spotted by a banker in the US that had a typo, and they stopped that transaction. So I hate to worry you, but that's the trustworthiness of that network. And there was another recent one where the SWIFT network in a bank was taken over completely for one day. Every single transaction was a kind of fake. They took over the bank, and the links to the SWIFT network, they were able to do whatever transactions. I can't remember the amounts, but it was a massive amount of fraud, and it's gone in an instance because the money laundering allows them to move the chain on, and it's very difficult to trace the money. It's often they often pay money mules to take money out of ATMs in different countries and so on. So the 81 million was never recovered there. In a Bitcoin infrastructure, we create a transaction that goes onto the blockchain. Miners agree to the consensus, and Bob signs that with his private key, and obviously everyone else can prove it was him because of his public key. Okay, so Bitcoin was created in 2019, and it was focused on having no central government or organization to broker in between. We can split it down into Satoshi if we want. What's fun is to look at some of the some of the things behind it. I thought this was an interesting finding fairly recently, and it's kind of, most people think that maybe Satoshi was from the US, but this analysis here on sorry, my machine's going a little bit slow. This analysis here analysed his work times. So using the Wayback Engine, it was possible to look back at all the posts and the emails that were made, and this was the times that he or she was working on it then. And you can see here, this is a dead period where there was virtually no postings. And the way you could look at this is that Satoshi was sleeping here, which would put him where? Where would, if he was sleeping here, where do you think in the world he would be based? This is London time, GMT. If this was sleeping time, where in the world would you put him or her?
US.
US.
Yeah.
East, west.
That'd be east.
San Francisco.
East.
San Francisco. San Francisco?
We got 8 hours difference.
Yeah.
8 for San Francisco and 5 or 6 for that. So it could play some or somewhere in there. But if you think that if he or she had a job, this was work time. So where would you place Satoshi now?
Here.
London.
Here.
Yeah.
Lisbon.
Yeah, London.
Morocco.
Lisbon, Morocco. Anywhere like that, even Central European time and so on. So if you propose that, then this is evening work and this is sleeping time and late work, maybe into the morning here. On there, basically the Sunday looked like kind of day off to some extent for that one. But what's even more interesting, this is the Genesis block here. And in the Genesis block, there is a bit of text in there. So it says, January 2009, Chancellor on the brink of second bailout of banks. And what's really interesting is that this is the headline on the Times on that day. And what's interesting is that the online version of this has a different headline. So if someone was in the US, they would probably not have the paper copy of this, but they would have the US version. So it's just something that was proposed that maybe Satoshi was from the UK, because you can see the title is taken from there. What's also interesting when you look at some of the curse words is that someone from the US wouldn't use that. That's a very kind of UK-centric curse word. The word honour, what's strange about honour there?
It's got the U in it.
Spelling. UK spelling.
Yeah. And no one in the US would ever spell it like that in there. So obviously I'm not saying anything here, but Adam Black is referred to quite often. If you're interested, this is a Peril code. This is one of his t-shirts. If you scan this, you get the Peril code for RSA in there. And in the Satoshi paper, he does refer to Hashcash within there, which was created by Adam Black. I have tried to get Adam as a guest speaker, but not confirmed yet. I'm not saying that it was Adam at all, but certainly there might be a pointer there, and I just think it's an interesting sideline to the normal discussion. Okay, so basically what happens is that each miner gets a reward for generating that hash that we saw, and it generally drops each time, and the last one dropped to just over 6 bitcoins for a miner who manages to get it. But if we're up about 50k for a bitcoin, then it's still about 300k if you strike lucky. And obviously you can do the calculation to the amount of electricity that you use up to see whether it's worthwhile for you to create a Bitcoin network. Okay, so this is eventually, as was said earlier, the Bitcoins will run out and there'll be none there, and the miners will stop mining from then. We'll have to find another mechanism for the consensus mechanisms. But it's not the only show in town, and Ethereum and so on are in there. Okay, so that's what the Genesis record looks like. So we can mine into that, and you can see there's only one transaction in there. From that, to that account that's the transaction hash, and that's the Bitcoin wallet address. But we can easily look at any of the block numbers. So we'll look at block number 1000 for that one. And we should be able to see this block 1000. Well, there wasn't too many in there, but we can mine in on each of the blocks. So we could look at the current block and have a look in there. So you can see there's about 12 minutes or so in there. That was quite a long time between those ones, but for each block we can actually look in there. So as we saw before, there's the timestamp, there's the Merkle root, the total volume in there, the rewards, 6.25 bitcoins, and here are all the transactions in there. And what we see is a transaction between one wallet and another. So this is going from this wallet to that wallet. Normally we start with a 1 or a 3 at the start of it for the wallet identifier. I'll explain that in a little minute. But there's a complete trace in it, and it's not anonymized, it's pseudo-anonymized. And if I know what your wallet is, then I can trace all of the transactions from there. So we could look at this wallet here, and well, there isn't too many transactions on that wallet, but for every address we can actually see exactly where the payments are made. You'll find that most hacks, and for things like ransomware payments, the wallets tend to split into 2, and then into 2 into 4, into 16, and then so on. So you find for money laundering, then almost the jump very quickly between wallets, and a payment will distribute itself and then eventually get cashed out from these individual wallets. So obviously law enforcement are watching these wallets all the time whenever there is kind of bad payments from cyber criminals. Okay, so there's a fee associated with every transaction in there, and so on. Okay, so there are some very large transactions that you see. This was a fairly large one in there. There was 2,000, but generally we're looking at some transactions that can be up to billions of dollars now. Typically, it's between these exchanges, large transactions. So you can see that we're increasingly seeing large movements of these bitcoins. And we can also get multiple wallets feeding into a single one in there. There's an example with a very big transaction there from this one going into that one in there. You can see that's a $588 million transaction. And then over time, it's generally picked up. There was a kind of peak before it dropped, it crashed the last time. But it really just kind of picked up early kind of 2013 and is a lot more settled now. For some reason, the Bitcoin graphs aren't showing the transactions correctly. If you want to do some research, but on the Bitcoin Explorer, you should be able to see the number of transactions per day. If this was working right, you should be able to look back at all time, but for some reason their charting isn't working. I tried with a few browsers today, and this is actually showing. So it's only showing the last few months or the last year in there for the number of transactions, and hopefully they'll get that fixed quite soon. So you'll be able to see the full history. So I didn't update that diagram within that. The transaction values, again, I couldn't get an updated version of this one, but it has peaks and troughs as we see big amounts being transacted. Obviously what happens is it gets inflated and then people all cash out, which can cause a crash, or a certain country in the world says that it's now illegal to transact, or there's now going to be regulation, or you have dirty money or something like that, and it can cause a crash from that. There has been cases of people pushing cryptocurrency on social media. I won't mention who they are, but you've obviously got to watch that. The value now is about 50k in there, and there are thousands and thousands of these. Mainly, the value is in Bitcoin and Ethereum, but obviously the other ones are doing pretty well. Polkadot is an interesting one here. Ripple does very well for that, but if you want, you can actually view them all. I think I've posted the link, but there are absolutely thousands, and anyone can create their own token if they want. Obviously, there's got to be some sort of value associated with it too. Okay, can I just confirm you can see that? Okay.
Yes.
Yeah, great. Okay, so that's the range of cryptocurrencies. So I'll go through this quite quickly, but there's a recorded lecture that you can go over. So the way it works, and we went into elliptic curve a little bit, and elliptic curve is typically the method that's used for most applications now, and less on RSA. So the way that elliptic curve works is that I can create my random private key, 256 bits, typically, depends on the curve. So I can have a sept 256 K1 is the curve that's used in Bitcoin. So it's a 256-bit value. But I can have another one, like I can have a 160 bit one, sept 160 K1, and that's a 160-bit private key that I would have. Okay, so the prime number that we use defines the size of the values that we're going to have, and we can have up to 256 bits. And I can assure you that it would take all the energy on the planet to be able to discover and more, and all of it. It will take trillions and trillions of years without a quantum computer to ever discover that private key from random searching. But if you've got a problem with your random number generator, then that's where the problem comes in, or when you have a static one. So please never let someone create your private key for you. So there was a hack on IOTA a few years ago where you went to the web page, and the site would create what's called a seed, or a nonce value for your wallet. But unfortunately, a copy of that was taken, and obviously someone with the copy of your private key or the nonce could actually go and eventually take money from your account. So watch for that. There was even a case of a company producing a printed wallet. I don't know if I've sent it on the Teams channel, and there was a backdoor in the QR code that was actually created for the wallet, which would allow someone to get into the private key. But this one should be kept secure and really typically protected with a password, and increasingly with hardware wallets through biometrics, fingerprints, and so on. But if possible, you should print it out and put it in a fire safe for that. For most wallets, you get 14 words. I think it's 14, and you write those 14 words down, and the 14 words are used with a certain method to recreate the private key. Can I ask, has anybody ever done that to store an encryption key?
Yes.
Good, excellent. I highly advise it. Obviously, if someone gets access to your safe, then you've got to watch that. But just in case you lose your phone or you lose your wallets, then that will recreate it. And I've certainly recreated wallets from the past with that. And I think in the lab, I've got an example of a wallet that you can try different passwords and so on. So you could try that. Then what you get is you get a strange base 58. What would we normally be dealing with? Base what?
64.
64. So does anybody know why we use base 58?
Is it des?
Is it what? Sorry, say again.
Is it 3 des?
No. It's a encoding method, so it's not even encryption.
Is it to eliminate some of those similar-looking characters like 0 and O and something like that?
That's right. So the 0 is gone. So if you look at an address, you'll only find there's an O and there isn't a 0. So those difficult characters that we all struggle with when we see are gone. So there's at least 6 of those. The 0 is obviously one that always is confusing, where it's a 0 and an O, especially if you use certain types of fonts.
Like uppercase I, maybe that sort of
uppercase I, yeah. So the I and 1 is obviously another one. So you can see there's a 1 in there. Oh, so there's an I. So yeah. So the uppercase I isn't there. Yeah, you're right. So I'll dig out the 6 characters that have been dropped. But we have a very strange base 58 thing, and that's the thing. It's called a WIF key, and that's your identifier for this key here. So when you print out your private key, it's typically in the form of a WIF format. If you remember elliptic curve, we take our base point, blah, 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 then we create our private key, and the public key becomes this base point added this many times, or multiplied, sorry, for that, and that gives us our public key. So that's the way that it works. We create a public key from that, and it's 512-bit because it's an XY point on the curve. So it's double the size of that. So you'll sometimes see it starting with a 04 to identify, and then if you count the characters after it, you'll get 512. The 04 identifies a public key. So always ignore the 04 if you're reading this back in, but that becomes the public key for signing that. It then goes through a few hashes to eventually give you, and base 58, to eventually give you your public key ID, which is the address that you're known as on the internet. There's 2 different types of these addresses if you look at Bitcoin. One begins with a 1, that's the older one, which is basically this one here. And the 3 is the newer one, and rather than pointing to a public key hash, it points to a script. So the script for the payment is the thing that makes the payment, and the hash of that payment is that address, and it makes it more extendable if we can link to a script rather than to the signature itself. Okay, so there's the one there for the address, and there's the hash of the message. Okay, so that's the process. The WIF key, private key. We create our signature, we create our public hash, and then we create the Bitcoin address. So this is what a transaction kind of looks like. There's the private key, the public key. So we identify that with a 04. Remember, there's the WIF, and that's what the address is here. We then get a signature here. So in elliptic curve Diffie-Hellman, the signature looks like this. And normally, whenever you look for a signature, you look for a 30 code. The 30 code identifies what's called an R and an S value. Those are the signature values on the transaction. The way to spot them is with the hex code of 30. So if we ignore the 49, 30 is what's called the DER format. If you remember back to digital certificates, we talked about the DER format for certificates. The 30 identifies what comes next is a signature or some definition of that. So if I take this bit here, hopefully I'll be able to check the signature on this, if this works. Okay, so I'm just going to paste that signature in there. Okay, just let me check that that's fine. Okay, so hopefully when I do that, there is the R value and there is the S value. So those two R and S values will validate the transaction, and these values are used with elliptic curve Diffie-Hellman, elliptic curve DSA to prove the signature, and it's an R and an S value from there. Okay, just give me a second while I get my presentation back. Okay, so that's the way that we would show, and always look for the 30 value if you can for the hex code. Okay, so Alice is sending to Bob. She discovers Bob's wallet ID or public ID, adds it into the transaction. She then signs with her private key, and then she puts that onto the blockchain, or she gives it into the network, and the miner will mine that and trust that as part of the signature. So another alternative that we can have is Ethereum, and with Ethereum what we have is we have a whole lot of miners, and with Bitcoin. So this was a recent survey of the mining process. And you can see that there are mining pools which have a fair percentage of the Bitcoin mining. What we've got to avoid is a 51% attack. If one mining pool managed to get 51% and more, they can take over the whole consensus of the network, and they can create transactions that they want. This is the current one. It's not quite getting to the same place, but you can see there are significant the companies which have a good amount of the mining success, and generally the hash rate goes up, and the higher the hash rate, the more difficult it becomes to create the hash. And in Bitcoin, as I said before, what happens is that you need to find the nonce value which relates to a certain number of zeros, and all we have to do is add a new zero on, and it will make the computational difficulty much more difficult. So every so often we add another zero on, and it becomes ever a bit more difficult for the miners to discover these things. So as I said, there's the zeros there, and there's the nonce value that's been discovered, and whoever gets that will get a payment for a reward, in this case 12.5 bitcoins for that. So Ethereum came along, and Ethereum introduced the concept of having smart contracts, and one of the first applications of that was with CryptoKitties. And with CryptoKitties you could actually buy a crypto asset and own it. And I think at the time people were paying hundreds of thousands of dollars for certain crypto assets, and this one looks a bit strange, and I wouldn't advise to take ownership of this one. But people were worried because at the time it was hogging the network and it was using a lot of space and Ethereum. So it kind of broke Ethereum around there, and we thought they would have got to the limit, but we can see after that actually transaction rates increased, so there wasn't really a problem with that. But obviously all of our blockchains have a certain limit that they can get to. So it was created by Vitalik, a genius, and someone who's really continued to innovate in the area. And as I said, it was hacked to create Ethereum and Ethereum Classic in 2016. And basically what happens is that we create a SHA-3 hash, and the miners, their work is to produce that hash, and they get paid back in gas. They get paid in creating the hash, and also in the amount of data that they process, which means that developers have got to keep their code small, because if they don't, then they're going to have to pay a lot of money, gas, to the miners. So it avoids denial of service, as was said there, and it avoids too much data, and to be efficient with the data, because the more data that you have, the more it'll cost you for that. But you can create small blocks, and these are then mined by the miners. Okay, so they get paid in gas, and gas is the way to incentivize the miners to perform these transactions. If the transaction fee is set high, there are lots of miners there to do it, of course, because they are incentivized by processing the high rates. But if you set your transaction fee too low, the miners might avoid you. So sometimes you've got to advertise your transaction at a reasonable rate. And if you go ahead and implement the lab today, you'll find the miners can be a little bit sluggish if you don't incentivize them. So you've got to advertise. But the miners only cash in what they've done. So even though you might advertise that a certain transaction has got high gas, then the actual amount of gas that the miner uses up will be the amount that's charged to you. So they return back the excess gas that they've used. So for that, so this is an example of the Ethereum blockchain. You use hex addresses rather than these base 58 crazy addresses, and there, so it's a much more efficient method for creating our little blocks. The one thing that came along with Ethereum was the concept of a smart contract, that you could actually run a trustworthy piece of code off the blockchain, so that Bob and Alice would maybe agree to something and it would be transacted no matter what. So Bob couldn't pull out of the transaction that was made. The smart contract would be responsible for making sure that everything happens. So in Ethereum, we use the Solidity language, which looks a little bit like JavaScript, and then we compile that into byte-ready code that would run off the Ethereum blockchain. So this is an example here of using Solidity and a small smart contract, and then we create the bytecode here. So this is the code that runs on the Ethereum blockchain, but we obviously need a way to deploy it, and one way we can deploy it is with this Web3 JavaScript integration. So this is basically taking the bytecode and running a piece of code that would allow it to be applied onto the blockchain. And if you run the lab today using the Geth infrastructure for Ethereum, you'll see how we can actually create these transactions and create the smart contract. And I've got examples of that if you ever wanted to do this as a dissertation. As a final point, so we have these Merkle trees and the signing process. As I said, we have our ECDSA as doing our signing for us. And in the end, we end up with these R and S values to prove the actual signature. We can then verify the signature against the public key. There's another little thing that has been added into Bitcoin, and increasingly we get lots of signers or lots of wallets sending to lots of other wallets. In the existing blockchain, you would need every single public key to be checked. So with the Schnorr method, we can actually merge these together with a single signing, and that would allow us to very quickly check all of these public keys together to be able to validate the transaction rather than having an individual public key in there. So we can merge keys together and we can aggregate them into a single public key that would prove the signature. And that was implemented fairly recently and has been quite a big success. And it happened here, I think. Yeah.
That aggregation and signing keys, is that essentially like a Merkle tree for signatures applied to your block rather than each individual one? I mean, it might not technically be that, but is that essentially
not quite. You can get Merkle trees that are like that you can have lots of private keys and you would prove each one. I'd have to think through what you just said there. I don't quite see it like that. It's more like just an addition. You just merge all of the keys together, and you can create a signal. You can create a single signature. But I'd have to think about what you said there. So I think this is the first one with the Schnorr. It's called the multi-sig. Was the approach there? Oh, that graphic is around the back there. And some cryptocurrencies don't want to be tracked. So Monero and Zcash are two examples that are fully anonymized cryptocurrency. So Monero was looking to use a ring signature. And with a ring signature, you can't tell who signed it, but you know that one of them did it. So you can trust something in there. So in this case, this person can tell that one of them signed it, but they can't tell which one was in there. So a ring signature allows Bob to sign a complete signature and without actually revealing that it was actually Bob that actually signed it. And Monero allows Bob to be kept anonymous because you can't actually track any address. So how does Alice or Victor become anonymized? Well, we create what's called a stealth address. And with a stealth address, you kind of say, you put a little tag onto the transaction to tell Victor that where to find the transaction as a stealth address. Victor then goes there and can get the money and transfer it into his own account. So in this way, both Bob and Victor are kept private. If you're interested, that's the crypto that allows that to all happen for stealth addresses. As a final thing, and I apologise for that graphic as came in there. Just let me change that a little bit. So public blockchains obviously have problems because all of the data is public and anyone can go in and view anything and so on. So there has been a move probably away from public blockchains towards what are called private or permissioned blockchains. And this way you can create your own network with your own peers and you can have your own ledger that can't actually be seen outside your infrastructure. So IBM created the open source IBM Hyperledger. Fabric is one of them, where you can actually create a permissioned blockchain. So nobody can transact in here unless they're allowed and unless they have public and private keys within the infrastructure. So that's the kind of comparison between Hyperledger and Ethereum. Generally, they're kind of supported by big organizations. Cisco and IBM are generally going for the Hyperledger approach. JP Morgan typically are going towards Ethereum as a public blockchain. But they have their own advantages. This one has got Go, Java, and Node.js, and this one has Solidity. It's probably easier to create your smart contracts or create your coding within inside there. And Hyperledger is really just an open platform. We use Fabric here. We also use Indy in terms of creating identities, self-sovereign identities within there. But the sawtooth for consensus. Fabric does this ledger approach, and there's lots of other ones, and it comes with a whole infrastructure of crypto from there. And although IBM have promoted it and supported it, it is open source and is available to everyone. What's interesting is obviously how do we link all of these blockchains together? How do we take a token, a Bitcoin token, and translate it into Ethereum or into Hyperledger and back again? Can we create an infrastructure that would allow us to be able to move tokens around, move transactions, and so on? Polkadot framework is interesting because it aims to do that kind of thing. It has a number of nodes, like a bridge between two blockchains. It can create relays that you would all take something from one network and move it onto another, and you can have things like cross chains in there. And again, you have these consensus rules. Fisherman is an interesting one in there, and this would allow you to be able to integrate all of the different blockchains together. Built on Rust, which is a very trustworthy infrastructure for coding and there. Okay, so it's a patchwork of lots of different things, and there's not one definite solution to any of these things. Does anybody have any questions on what we've covered at all?
I have one, Bill, about transaction value.
Yeah.
Not transaction value, so the cost of transaction. I don't know if it's changed now, but are things like Bitcoin fundamentally unusable for small transactions, like going to buy a packet of sweets or something, because the cost of the transaction outweighs the small cost?
Yeah, and you would go more for the kind of permissioned type approach there. IOTA is one example of having. You can create your own permissioned. You can create your own blockchain infrastructure, and the fees are virtually zero. So for small things, you're right. You wouldn't use Bitcoin because it's just not. And the worry is that you get a decimal point wrong. you could be paying $10,000 for some sweeties. So you're right. Okay. So we'll do a quick wrap up. I don't think we've got too long. What I might do is keep some of these questions back until the evening session. But if you go ahead and open up Mentimeter, and let's see. For me, I use Apple Pay. I don't know if you trust it, or Google Pay. I quite like it because it's got face recognition and fingerprints, and I can store my credit card on there. But obviously contactless is the one that's used most often for that. And good, cash. Good. I'm glad some people still use cash there. But obviously in the pandemic, then the usage of cash is obviously just. I can't remember the last time that I used cash. Okay, so we're mainly in the region probably of using contactless payments for that. Do you trust cryptocurrencies? Not too bad. Nobody's went for high yet. So generally not too bad in terms of trust. Nobody has high trust levels. Some people have very low and low, but we're kind of on the fence mainly in terms of our trust level for that one. And which one would you use out of those ones? I appreciate if you've not came across them before, then you might not know which of these are. But yeah, Bitcoin and Ether. Oh, got a Litecoin. Good. So there is a business model that says that I could pay you some money if I can crypto mine on your computer while it's not doing anything. It happened quite recently that there was a JavaScript code in Starbucks, I think it was in Brazil, that crypto mined your computer when it connected to the Starbucks network. Unfortunately, there's a bug in it so that your CPU went up to 100%. The recent crypto miners don't take as much of the CPU, but it's a valid business model. And yeah, so maybe if you were incentivized to leave your Sony PlayStation on, then maybe you would accept that. But some people, it's a scary thought to have a crypto miner on their computer at a given time. So you can see there's the jury's out in that one. So are cryptocurrencies mainly used by criminals? Are they free people from the banks? They're mainly for people to hide tax. Cryptocurrencies will never take off, or cryptocurrencies are a faster way of making payments. Good. Oh, well, we've got one person went for never take off. Interesting. And we got hiding tax is another one. If HMRC eventually publish something on crypto assets for individuals, I've not seen one yet for businesses. But obviously tax authorities need to understand that cryptocurrencies are almost like stocks and shares. So mainly we believe that they could free people from banks. This is interesting. And cryptocurrencies are the future, a bubble that will burst, never going to match existing finance infrastructure, or a major risk for the future. So we got quite a difference of opinion here. So yeah, the bubble that will burst, and who knows where it's going to end up. When I last looked at Bitcoin, it was 10k, and I think it's now at 50k. Times 5 is just crazy for any asset to go up for that, because you get something like 0.5% APR in the banks just now. Bitcoin, you could be getting that in a single minute. Okay, so that some of us think it might be a bubble that bursts, or it could be the future, and so on. I don't think you'll never achieve the trustworthiness of banks. Banks are all about trust. You trust that bank to look after your money, and then you know that if something goes wrong, then they'll as you say there, they'll reduce the risk for you. So what are some of the words related to cryptocurrency? Keep it clean. Freedom, risk, safe, decentral, anonymity, database, ransomware, yeah, secure, free, hidden, yeah, anarchy, wow, secrets, privacy, freedom seems to be the most popular word there. Smart, wasteful, yeah, certainly Bitcoin wastes a lot of energy waste. I think it was looking to, just a few years ago, all of the energy in Ireland is used up through Bitcoin, and it's increasing rather than reducing, evolving, unpredictable, and so on. Gambling, interesting for that. Yeah, you gamble. Yeah, that's certainly true. Okay, so we've got 10 minutes, so we'll have a quick go at this test this week to see how you get on. Okay, so if you could just register. Now, it's a bit of fun. I do say that I don't have any cryptocurrency, so I purely have outlined the technical nature of cryptocurrency and do not recommend any of them or using cryptocurrency at all. Okay, so let's have a go at this one. Okay, so just waiting to start. Okay, who was one of the cypherpunks? Hal Finney, Eric Hughes, Ron Rivest, or Tim Berners-Lee? Tim Berners-Lee is promoting a decentralized web. If you've got some time, have a look at his spin out. I think that is associated with Ron Rivest from our Len Edelman. Haha! Yeah, good. Well done. I caught you there. It was Eric Hughes as one of the cypherpunks. Okay, so let's see. Only 5 people got that one right. And it looks like Casper, Josh, Sam H, Dragonite, and Ribbit. And everyone else got 0, unfortunately. Okay, I didn't think that one was going to trip you up so much, but yeah, that's a good one. So who's the A in RSA? Hopefully most of you will get this one right. Leonard Edelman, Len Ankerman, Larry Edelman, or Lizzie Aderman. So if you all attended the great guest talk by Len, then it was Len Edelman is the A in RSA. So hopefully you did a bit better there, and O did well, and Casper did well again, and Anonymous, and Hula Hoop, so on. So it's quite a lead there, but we lost 3 people who got the first question right, but Batman's back in there in 3rd place. So we've got two leaders just now, well at front of the rest. Let's see how you can get on for this next one. So which is not a public key encryption method? RSA, elliptic curve, Elgamal, or AES? Which method would you not use on a kind of blockchain infrastructure? And so the method is AES, which is symmetric key. RSA, elliptic curve, and Elgamal are all public key methods. The first 2 are mainly used. Elgamal can be used and is actually used in ECDSA, but not going into any great detail. The AES method is a symmetric key encryption method. So let's see if Casper and Anonymous are still top. Anonymous was a little bit slower there, but Casper is way out in front. And Eric coming into the top 10, which is good. Okay, who co-created Ethereum? Vitalik Buterin, Vitalik Buterin, Buterin Vitalik, or Buterin Vitalik. And it was Vitalik who created it. Hopefully we might get a guest talk from him sometime. Probably not this year, but yeah, I mean, go and listen to any of his talks, please. Really interesting. Visionary. Oh, and Casper fell at that one there, and Anonymous is probably top now. Oh, it's a bit clearer now. Bally McFootball doing well, and Eric moving up. Batman Herman was the fastest there, moving up. So we're getting a bit of a evening up now, which is good to see. Which is a permissioned blockchain? Permissioned blockchain, Hyperledger, Bitcoin, Ethereum, Steam, or Waves? And it's Hyperledger. is the permissioned. All of the other ones are public blockchains. So let's see how Anonymous got on. Casper back there again, might go top again. Jellybean doing well. Batman slipping back a little bit, and Herman moving up to third place. So not too much, 40 in it. And Anonymous is just dropping back a little bit now. Question number 6. I did mention this, but do you know which country introduced a blockchain act? Liechtenstein, Estonia, Finland, Jersey, or the UK? It's more general knowledge, this one. It was little Liechtenstein. The UK is a long way away from ever creating a blockchain act. Probably Jersey would be in there as close, and maybe Estonia, but the answer was Liechtenstein. And Anonymous back there, probably back top again. And Master was the fastest. Oh, Master really moved up for that one. Bob wants to send Alice some bitcoins. Which key does he use to allow the transaction? His private key, his public key, her private key, or her public key? Which key is important to enable the transaction? It's Bob's private key, of course, that he will use to sign it. Let's see how we got on. Jellybean and Master dropped that one, and Batman didn't do so well. Eric is coming back. It's still in 10th place, and yeah, Herman really moving fast up to the top. And the next one. Bob wants to send Alice some bitcoins. Which key does Alice use to prove the transaction? Bob's private key, public key, her private key, her public key. Which key does she use to prove that the transaction is correct? It should be Bob's public key, of course, to prove that. Okay, so Anonymous tripped up there a little bit, and Herman, I think, should be top. And Ballymuck Football really making a move, and Jellybean doing well there. Only 3 more questions. We'll finish them anyway. Roughly how many bits does an elliptic curve public key have? Like a typical one: 128, 256, 512, or 1k bits. A typical elliptic curve, like that we'd use in Bitcoin, a public key has an XY, so it has 512 bits. The private key is this one. The public key has 512 bits because it's an XY coordinate. And Anonymous back in there again, but Herman doing well, and Casper back up there again. Casper and Anonymous still doing very well, and 400 points difference in between first and second place. Who's not one of the people who was involved in the creation of Bitcoin? Adam Black, Ralph Merkel, Hal Finney, Whitfield Diffie, or Satoshi Nakamoto? Which of those would you not necessarily associate with Bitcoin? Adam Black, yeah. Ralph Merkel, yeah. Hal Finney and Satoshi Nakamoto were all kind of involved with it. Whitfield Diffie obviously produced amazing work, but not quite related to Bitcoin. So Whitfield Diffie was the right answer there. Let's see how Herman got on. Oh dear. And Casper is back at the top again, possibly. Wow, this is quite a challenge at the top there. Casper, Herman, and Anonymous, and there Eric moving up a little bit. Sam H making the move. Final question. See how you get on. Final question. For a Bitcoin signature, what are the 2 values called? R and S, E and B, P and S, or pub and sec? And the answer is RNS for there. That's our signature value. So let's see the final. Herman, Casper, or anonymous, and yeah, Casper got it right. So it looks like Casper is top, followed by Herman and anonymous, and a little bit of movement there. So who's Casper?
Hi, Bill. That's me.
Well done. Yeah, who's Herman? Oh, no, that's Herman. Hi, Herman.
Hello.
Yeah,
Do we still
well
get
done.
mugs?
It was close. Oh yeah, do you want the mugs? Yeah, you know what? I forgot. Let me near the end of the module send out some mugs, and I'll make sure that those who have done well here get them. So I'm sorry about that.